module, you will learn about the moment of inertia of a rigid body. The kinetic energy of a particle of mass m and moving with a constant speed v along a straight line is given by kinetic energy corresponds to its linear motion. KL is equal to half mv square, equation 1. If the particle is rotating about an axis with an angular speed omega and at a perpendicular distance r, then its linear speed v is equal to omega r. The kinetic energy of the rotating particle is Kr is equal to half mv square, which is equal to half m into omega r whole square, which is also equal to half mr square omega square. Let this be equation 2. Now, consider a rigid body of mass m rotating about an axis with a constant angular speed omega. We can treat the rigid body as a system of n particles of masses m1, m2 and so on mn, which are located at perpendicular distances r1, r2 and so on rn from the axis of rotation respectively. Since the rigid body is rotating at an angular speed omega, the angular speed of all the constituent particles are also equal to omega. The linear speed of each particle can be found using the relation v is equal to omega r. For the ith particle, the linear speed vi is equal to omega ri. Then, kinetic energy of the ith particle is Ki is equal to half mivi square, which is also equal to half miri square omega square. The rotational kinetic energy of a rigid body is the sum of kinetic energies of the constituent particles. K is equal to sigma Ki, which is equal to sigma half miri square omega square, which is also equal to half into sigma miri square into omega square. If we define a new physical quantity, I, that is equal to sigma miri square, then the rotational kinetic energy of a rigid body, K, is equal to half I omega square. Let this be equation 3. Let us compare the two equations 1 and 3, which gives the expression for linear and rotational kinetic energy of a body. The angular speed omega of equation 3 is the rotational analogue of the linear speed v of equation 1. Then I must be the rotational analogue of mass m in linear motion. I is called the moment of inertia of a rigid body. We know that the mass of a body is the measure of its inertia. Let's see what happens when 3 different masses are placed in front of a compressed spring. We observe that the force exerted by the compressed spring acting on the bodies of different masses is the same for all of them. But when the spring expands, the 3 different masses move through different distances. That is, the greater the mass of a body, the less is the change in its state of linear motion. Or, in other words, the greater the mass of a body, the more is its resistance to any change in its linear motion. Similarly, we can understand moment of inertia as the measure of resistance offered by a body to any change in its rotational motion. That is why moment of inertia is also known as rotational inertia. Let's observe a rotating platform. We see that when a small weight is placed at one end of the platform, its angular speed of rotation decreases. If one more identical weight is placed on it, the angular speed decreases further. This implies that the moment of inertia of a rigid body depends on the mass of the body. If one of the weights is shifted as shown, then we observe that its angular speed of rotation increases. This means that the moment of inertia of a rigid body also depends on the distribution of mass about the axis of rotation. Now, if AB is the axis of rotation, and if the platform is tilted slightly as shown, it rotates about a different axis of rotation, AC. But the angular speed of rotation about AB changes, implying that the moment of inertia depends on the position and orientation of the axis of rotation. The SI unit of moment of inertia is kilogram meter square, and its dimensional formula is m raised to power 1 and L raised to power 2. Consider a system of 3-point masses, each of mass 0.1 kg, 0.2 kg and 0.3 kg located at 1, 2, 2, 3 and 3, 1 respectively. The moment of inertia of this system of 3 particles about the x-axis, Ix, is equal to sigma m(I)y(I) square, which is equal to m1y1 square plus m2y2 square plus m3y3 square, equal to 0.1 into 2 square plus 0.2 into 3 square plus 0.3 into 1 square, equal to 0.4 plus 1.8 plus 0.3, which is equal to 2.5 kilogram meter square. Similarly, the moment of inertia of this system of 3 particles about the y-axis, Iy, is equal to sigma mixi square, which is equal to m1 x1 square plus m2 x2 square plus m3 x3 square, equal to 0.1 into 1 square plus 0.2 into 2 square plus 0.3 into 3 square, equal to 0.1 plus 0.8 plus 2.7, which is equal to 3.6 kilogram meter square. Note, the moment of inertia of a rigid body cannot be calculated by assuming that the whole mass of the body is concentrated at its center of mass. For example, the center of mass of the system of particles discussed earlier is x is equal to m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3, which is equal to 0.1 into 1 plus 0.2 into 2 plus 0.3 into 3 by 0.1 plus 0.2 plus 0.3, equal to 2.33. And y is equal to m1y1 plus m2y2 plus m3y3 by m1 plus m2 plus m3, which is equal to 0.1 into 2 plus 0.2 into 3 plus 0.3 into 1 by 0.1 plus 0.2 plus 0.3 equal to 1.83. If we assume that the entire mass of the system is concentrated at its center of mass, then Ix is equal to my square, which is equal to 0.6 into 1.83 square, equal to 2 kilogram meter squared. This is different from the actual moment of inertia of 2.5 kilogram meter squared. Hence, we see that the moment of inertia cannot be calculated by considering the center of mass. If the distribution of mass is continuous, then the moment of inertia is expressed as I is equal to integral of r squared dm. This property of moment of inertia has many practical applications. A good example is a flywheel. A flywheel is a mechanical device with a high moment of inertia. Because of its high moment of inertia, it resists any change in its rotational motion. Flywheels are used in automobile engines and steam engines and help to gradually change the angular speed of the wheel. You have now reached the end of this module. In this module, you learned that the moment of inertia is defined as I is equal to sigma MIRI squared. The rotational kinetic energy of a rigid body is K is equal to half I omega squared. I is the rotational analog of mass m in linear motion. I is called the moment of inertia of a rigid body. The moment of inertia is the measure of resistance offered by a body to any change in its rotational motion. Moment of inertia is also known as rotational inertia. Moment of inertia of a rigid body depends on the mass of the body, distribution of mass about the axis of rotation, and the position and orientation of the axis of rotation. The SI unit of moment of inertia is kilogram meter square, and its dimensional formula is m raised to power 1 and L raised to power 2. For a continuous distribution of mass, the moment of inertia is expressed as I is equal to integral of r squared dm. The flywheel is a mechanical device with a high moment of inertia, and so it resists any change in its rotational motion.